All right, so continuing on our journey of applying calculus to 3 dimensions, we have now arrived at derivatives and integrals of vector functions. And so you might be thinking, hold up, friend, we are about to take the derivative of something with respect to time, and then we're going to integrate with respect to time. I feel like when we did integrals and derivatives, we were talking about slope and area. How does that apply here? Great question. No, I'm kidding. But it is something we want to talk about in this sense. So our derivative still is kind of representing a rate of change, but since our derivative ends up, as this talks about, applying to each component, it's kind of the rate of change in each component, x, y, and z. And we can still create a tangent vector, as we will in a second. I do want to remind you that the definition of derivative is still here. That is the OG formal definition of derivative, like you did in BC Calculus. Will I make you do it that way? No, I will not. So you can just put a big old smiley face by this guy and be like, thanks for showing up, but we have moved on. Okay? Anyway, so taking the derivative, you take the derivative of each component. That makes sense because we just talked about the fact that if you were taking the limit of a vector function, you take the limit of each component. So that, since the derivative is a limit, we apply that to each component. Okay? We also call r prime of t, because the derivative of a vector is another vector, we're actually creating a tangent vector. Okay, so we're creating, instead of in the past, when you took the derivative of a function, you got some kind of slope, but you still had to write the equation of the tangent line. We're going to do that in a second. We're going to write the equation of a tangent line, but we are creating something. We are creating a vector that is tangent to the curve. Okay, so if I had a curve like whoop, okay, and I was taking the derivative at this point, okay, I am creating technically a tangent vector. Okay, and usually it is going in the same direction as the curve, usually. Because that depends on the function, but regardless. Okay, a tangent vector cannot be the zero vector. That's another important thing. And we use the unit tangent vector. Okay, again, unit tangent vector, a vector divided by its own magnitude, unit vector. For some very specific things in this chapter, but usually we give it a special name. It's special enough to have a big T of T notation. So let's do a little bit of examples with this. Okay, let's find that unit tangent vector for this curve, t squared negative t cubed plus t to the fourth at a certain point. Okay, so first I need the derivative, r prime of t. Okay, so our good old-fashioned derivatives, power rule, 2t, 3t squared, 4t cubed. Now, I want to warn you, if you try to take the magnitude now and find the unit tangent vector in general, it's I guess not in this case, but in the future it could be kind of a mess. So before I find the unit tangent vector, since I do want it at a specific point, let me find the derivative vector at that point, or the tangent vector at that point, because finding the length of this vector looks a lot easier than finding a length of this vector. So our magnitude of r prime of 1 is the square root of 4 plus 9 plus 16, which is the square root of 29. Okay, good times. So our unit tangent vector at 1, okay, make sure you're saying at 1 because we are very specific about plugging that in, okay, will be 2 divided by square root of 29, negative 3 divided by square root of 29, 4 divided by square root of 29. So those of you with physics applications on the brain, we will use the tangent vector like this, like the unit tangent vector, a little bit later to do a very brief application into tangential acceleration. Regardless, here it is, not that hard to find, unit tangent vector. Okay, now I wanted to also show you an equation or a problem where we actually found the tangent line, and so we got to see what that looks like in multivariable calculus and kind of compare it to what it looked like in BC calculus. So to find the equation of the tangent line, remember we need the equation of a line. And we'll use the vector form because that's probably the nicest. Plus TV. Okay, how do we make the equation of a line? We need an initial point. Okay, well, they gave it to us. Here it is. So my R naught is going to be at -1, oops, -1, 1, 1. But they didn't give me a time. So I don't know what time to evaluate my derivatives at, right? I could find R prime of t by taking the derivatives of each of these components. So 2t, 2t, 1. But this is not a time. I don't get to plug these. This is x equals -1, y equals 1, z equals 1. I don't get to plug that into values of t. That doesn't work. But I can just take a second, okay, set each of these equal to the original functions and solve for t. And in this case, I guess I'll show you that really quick. -1 equals t squared minus 1, 1 equals t squared plus 1, and 1 equals t plus 1. So all of that, regardless of which equation you use, you're getting that t should be equal to 0. Okay, so now we're ready to evaluate our derivative and use that as our direction vector for this line. Because the tangent, okay, our derivative gives us the quote-unquote slope of the tangent line, right? That slope is now this direction vector. So our vector equation, oh, they say parametric equation. I lied to myself. Okay, we'll write it in vector form first, and then we'll write it in parametric form. Okay, so R naught, so -1, 1, 1, plus t times direction vector. So I take t equals 0, and I plug it into my derivative, and I'm getting 0, 0, 1. Okay, so my tangent line in parametric form is x equals -1 plus 0t. You don't have to include that, but I'm being fancy. Plus 0t, and then z equals 1 plus 1t. Ta-da, there it is. All right. Second derivative, same thing. It doesn't quite, the second derivative doesn't quite tell us about concavity anymore as much. It gets a little bit complicated to think about concavity when you have a lot of different directions to look from. Like, are we thinking about concave, not just concave up and down, but are we thinking about concave left and right? So a good thought experiment here, but remember just your skills for taking derivatives. Okay, we're given derivative of cosine. Ooh, check your signs, haha, because it's sine. Okay, 1, 3t squared. Second derivative, we've got negative cosine of t now, 0 and 6t. Okay, easy peasy. All right, what else are we looking at? Oh, we are also looking at the fact that we need a smooth curve. Okay, so that's exactly what it sounds like. No like bumps along the way. Doesn't make a nice smooth path through space. But we define that using two different things. It's smooth if the derivative is continuous and the derivative is non-zero. The derivative vector is not the 0 vector, except maybe at the end points. Okay, so how would we check that? Well, how do you check if the derivative is continuous? Well, I think we're not going to have to check every point on the interval. I think it's enough to prove that there are no discontinuities on the interval. So my derivative here, r prime of t, is e to the t, 2t, 3t squared. Okay, is that continuous on 0 to 1? Yes. Okay, so this is continuous. And you're allowed to just state that. You could also be like, it's continuous because it does not have any discontinuities. But that feels a little redundant. So you're welcome to just say that it is continuous on the closed interval 0 to 1. Now, is it the 0 vector on 0 to 1? Okay, that means does the whole thing, does r prime of t equal the 0 vector for some t value on 0 to 1. We get pretty close, right? We get pretty close in the sense that we could get the vector 1, 0, 0, but there's no way for us to make all 3 components equal to 0 using the values 0 to 1. So therefore, there is no way, okay? So and r prime of t does not equal the 0 vector on 0 to 1, including the endpoints. Remember that the definition says it could be equal to 0 at an endpoint, and that would still count as smooth. But we're good on this case to include the endpoints. So the derivative vector does not equal the 0 vector on this interval. Therefore, this curve is smooth. Okay. And that comes in handy later when we end up taking a lot of integrals. I feel like a lot of what we're doing right now is laying the groundwork. We're building a lot of secret tools that are going to make our lives easier in the future. So hold on. Hang on to these tools. Keep them in your brain. Here are a bunch of derivative rules. Okay, so the derivative of the sum of 2 vectors is their derivative separately. You can factor out a constant. This one is a little weird. What I want you to know is that this is a vector function. F of t is just a regular function. Okay, so it's able to be factored out because it's not a part of like the actual vector function. That's why we can factor it out. Multiplication. Okay, the multiplication derivative rule still applies. That is for the dot product. This one is for the cross product. Okay, so just be really careful about how you do that. These should have little dots still in there. So put some dots in there if you have notes. Okay, we didn't just get rid of the dot product. Okay, and then this is our version of the chain rule where there is a function inside of the vector function. All right, integrals, definite integrals. Here is the idea that when you're taking the integral of a vector function, you're actually just taking the integral of each component separately. Okay, and the fundamental theorem of calculus still holds. Okay, so we're still going from final minus initial. And so this is where I want you to say kind of like, okay, so before when we integrated under a curve, we like found all that area. How does that apply now that we're integrating in space? What we're doing right here is just the net change of each component. It's not necessarily the area under the curve. That's gonna be a little different. In order to do that, we would not need to integrate with respect to time. We would need to integrate something with respect to the arc length. So that's going to be a little bit more challenging, a little heads up for the future. But right now, we're just looking at this integral as the net change of each component. Okay, how much did we change over this amount of time? Okay, so quick 2 examples here. Find an indefinite integral. I wanted to remind you of this one. So indefinite integral of r of t with respect to time is the integral of each one separately. I'm just going to leave it actually as 5, 6t, 2t cubed dt. And the integral of a vector is still a vector. Okay, so I'm getting 5t, and then I'm getting 3t squared, and then I'm getting like 1/2 t to the 4th plus c. Plus c, my friends. It is still happening, but now c is a vector. Okay, each component could be applied differently to, each component of c could be different. Okay, so we're going to write that, if I wanted to write it all as one vector, as 5t plus c1, 3t squared plus c2, 1/2 t to the 4th plus c. Cool. C3. Okay. All right, and then of course a definite integral for the road. Okay, integrating this function I am getting t squared over 2, t to the third over 3, t to the fourth over 4, and I am evaluating this from 0 to 1, which means I'm actually subtracting two vectors. So I'm subtracting the vector 1/2, 1/3, or I'm subtracting from the vector 1/2, 1/3, 1/4. Well, I'm just subtracting the 0 vector. So my answer is 1/2, 1/3, 1/4. Okay. All right, more examples in class, but welcome back to calculus. Hopefully that wasn't too traumatic, but derivatives and integrals, we're ready